So now we're going to look at deriving Bayes' theorem, but we're going to keep things relatively simple by focusing purely on discrete random variables. So what do we mean by that? Well, up until now, we've been fairly casual with our notation. And we've used this sort of notation to say, well, it's the probability of x. But if we're going to be more precise, what we should really write is this. Let's say probability of capital X being equal to small x. So this capital X, let's say that is our random variable. And then the small x is a particular value. So for example, if we're throwing a dice, then capital X represents the outcome of the throw of the dice. Then small x represents a particular value. So this is the outcome of the throw, and then small x could take any values from 1, 2, 3, 4, 5, or 6. And so that's how we write down the probability that the throw of the dice will be equal to a particular value. And then this has to obey one of the laws of probability states that if we sum this over all possible values of small x, then it will be equal to 1. So if we look at the probability that the dice could take values from 1 to 6 and we add them all together, then even if it's not a fair dice, then the summation must be equal to 1, because we've added together every possible event that can occur. So we're going to focus on these discrete random variables, and we're going to use this more precise notation. And what we're going to do is we're going to first look at what we call marginal probability. And then we're going to look at something called conditional probability. And then from there, it's actually very easy to derive Bayes' theorem. It's really just 1 or 2 lines. And of course, we're using the word discrete because our random variable can only take discrete values as opposed to continuous values. So now we look at what happens if we have a 2-dimensional distribution or problem. So let's say we have on our horizontal axis, we have 3 possible values of x. Again, discrete values, so let's say x1, x2, and x3. And then on this vertical axis, y. For example, we're going to say there's 2 possible discrete values that y can take. And then we have 6 points, each of which represents a particular event. And the height of that point coming out of the page represents the probability of that event occurring. So, for example, this point here, this represents the probability that our random variable x will be equal to x3, and our random variable y will be equal to y2. So what we have is a probability distribution over these 6 possible events, and just as we saw earlier here, it has to be true that if we sum over all of the possible events, then that summation must be equal to 1, because we're summing the probability of every possible thing happening. So in general, for this 2D probability distribution, if we look at the probability that random variable x is equal to xi and random variable y is equal to yi, and then we sum those over I, so all the possible x's, and then sum over all the possible j's. So in this case, we have I is equal from 1 to 3, and j is equal from 1 to 2, that summation must be equal to 1. And so now we ask ourselves the question, well, what is, let's say, look at this, what is the probability that random variable y will be equal to y2? And we're not going to condition that on x. So if we've not specified an x, what we need to do is we need to sum together all of the possible different events that could lead to our random variable y being equal to y2. And there's 3 events here. So that is equal to, well, our first event is that random variable x is equal to x1 and that random variable y is equal to y2. So we're going to look at this point first. So that is probability of x1 occurring and y2 occurring. Then we also have a second event here, x2, y2. This is the probability of x being equal to x2 in this case, and then y being equal to y2. And finally, the third event is here. So that is the probability of x being equal to x3. And again, y still being equal to y2. So we've summed over all the possible events that lead to y being equal to y2. What we have in general, so let's say this implies, in a more general sense, the probability of y being equal to, let's say, some discrete value, yj, is equal to probability of, so I'm going to leave some space actually, the probability of x being equal to discrete value xi and y being equal to yj, but summed over all the possible values of x. So all this is a general statement of what we've written here. And sometimes the language that you might see would say that what we've done here is we've marginalized over x, and that this is a marginal distribution, or marginal probability rather. So we've completed step 1 and we've looked at what marginal probabilities are. So now we need to look at what conditional probabilities are. So we go back down here, and as an example, we're going to ask ourselves, what is the probability that random variable x is equal to xi, given that, or conditional on, let's say for this example, random variable y is equal to y1. So if we look here, these 3 events are all events where y is equal to y1. So if we come, let's say we're going to go down here, I'm going to plot another thing. So this is going to be x again, and we still have our 3 possible values. x1, x2 and x3. And then what we're going to do is the height of each of these points coming out of the page, we're going to plot on this vertical axis here. So let's just say that it looks something like this, just as an example. So we might think that this is the probability distribution of x conditional on y being equal to y1, but actually it's not necessarily, or not in general, a valid probability distribution, because if we sum each of these heights together, we're not guaranteed for the summation to be equal to 1. So in other words, we're breaking our one of our laws of probability, that if you sum over all of the possible events, then that summation will be equal to 1. So what we've got here, this is correct up to a constant of proportionality, essentially. So what we need to do is we need to take this and we need to normalize it so that if we add together these values, then they will be equal to 1. So we're going to say that probability that x is equal to xi, given that y is equal to y1, so that is equal to the probability that x is equal to xi and y is equal to y1. So that term there is the height of these stems. Then we're going to normalize it, and so we're going to say divided by the probability that x is equal to xi and that y is equal to y1, but summed over all the possible values of x. Okay, so that means that if we sum this term over all the possible values of x, then we'll end up summing this term over all the possible values of x, and this numerator will then cancel with the denominator, and so we'll be left with 1, which is what we want. And then finally, we also know that from our definition of marginal probabilities, we can actually write this in a slightly simpler form. So the numerator stays as it is, so we have probability of x being equal to xi and y being equal to y1 divided by, and then knowing or applying what we know about marginal probabilities, we can now write the denominator as simply the probability of y equal to y1. Okay, so we now have looked at conditional probabilities, and in fact we'll show now that we've got everything we need to derive Bayes' theorem. So first of all, what I'm going to do is take our expression for conditional probability that we've got here. I'm going to write it in a slightly different way and also a slightly more general way. So I'm just going to say that the probability that x is equal to xi and that y is equal to, so let's say to be more general, yj in this case, is equal to, and all we're going to do is rearrange the expression that we have here. So it's equal to the probability that x is equal to xi conditional on y being equal to yj multiplied by the probability that y is equal to yj. Right, so now we've derived this, we can also say that, so all I'm going to do is swap these terms around. So rather than x equals xi, I'm going to say what's the probability that y is equal to yj and x is equal to xi. And again, I'm just going to be swapping these terms essentially. So that is equal to the probability of y being equal to yj given x equal to xi multiplied by the probability of x being equal to xi. And then really the only key thing we need to notice here is that these two things are the same. The order in which we write these terms doesn't matter. So these have to be exactly the same. There's no concept of order here. Probability of x being xi and y being yj is the same as the probability of y being yj and x equals xi. So from that we know that these two terms must be the same as well. So the easiest thing to do here is to elaborate on that. It means we know that this term on the top is equal to this term on the bottom. And then we're really just one step away from deriving Bayes' theorem. So I'm going to divide both sides of this equation by the probability of y being equal to yi. So we end up with our first term, probability of x being xi, given y equal to yj, is equal to, so this stuff. So probability of y being equal to yj, given x is equal to xi, probability of x equals xi. And then, like I said, I've divided both sides of this equation by the probability of y being equal to yj. So that ends up here. And so there we have it. That is Bayes' theorem for discrete random variables.